On your syllabus it has experiment 5 and 6. The doing in lab is experiment 6 for the most part. Experiment 5 is about IR spectroscopy, which we'll talk about here in a little bit, and it gives you the instructions for collecting spectra. But the actual doing the experiment is experiment 6. You have a quiz this week. Next week is fall break, so we don't have lab on Tuesday, well, we don't have school on Tuesday, so we don't have lab on Thursday, okay? But your experiment 3 report is due, so find out from your laptop when that is due. Because of fall break next week, we have open lab Wednesday, Thursday, Friday. So Wednesday is normal time, 9:30 to 3:30. Friday is normal time, 9:30 to 3:30. Next Thursday, because we don't have a scheduled lab session, we have the labs open, and they're open from 9 a.m. to 5 p.m. next Thursday. Okay. Next Wednesday is Monday's schedule. There's no lab lecture next week because we don't have lab next week. Okay. But instead, go to workshop because you will have workshop for lecture next week. All right. And then in 2 weeks, so when we see you again in lab after this week, we will be doing experiment 7. It's a 2-week experiment. We're going to do part 1. But make sure you have the pre-lab for experiment 7 all complete when you come to lab in 2 weeks. Okay? All right. Experiment 6, we're going to be using unknowns again. And it's a little bit different than experiment 1, where you had a list of possibilities to choose from. This time you don't have a list of possibilities to choose from. You just have possible functional groups that could be in your unknowns. So it could be an alkane, an alkene, an alkyl halide, or a ketone. Sorry, or alcohol or ketone. So I'm going to go through the steps we're going to use for you to help figure out what your unknown is. So you're going to get to a point where you figure out what functional group you have, and then you need to get to the point where you actually identify what exact unknown you have, okay? So the first thing we need to do is determine the physical constants. And if you need a melting point, you already know how to do that. If you need a boiling point, you haven't necessarily, you've done something similar, but not exactly what we're going to do this week, okay? So for determining a boiling point, we're going to use a piece of glassware that's in your drawer that you haven't used yet. It's this little piece that is this all-in-one simple distillation apparatus, okay? So it's all the pieces for a simple distillation all in one piece of glassware. And if you have a liquid, you would put your liquid in here with stir bar, put it in a heating mantle because you don't know what it is, so you don't know what the boiling point is. There is a stopper in your common equipment that will help you get your thermometer to fit, so it's a #1 stopper, fit into your apparatus. And then you're going to use eventually your test tube that has a side arm on it to collect your whatever distills over, okay? Now what you may get in setting up this distillation is a little bit of liquid that comes before it settles at a certain boiling point. So you'd want to collect that in a regular test tube and then put your sidearm test tube on to collect the steady boiling liquid, okay? Because that should probably be what your pure unknown is, all right? So your condenser for this is this arm here. What you can do is put a little bit of a wet paper towel on this arm before it goes into the sidearm test tube, and that can help condense it. The pipe cleaner that you have in your drawer, you can use that to tie the paper towel on that arm so it stays on there. And then when you're doing this distillation, you want to be careful. You don't want to go to dryness, so make sure you stop it before it is completely empty in your distilling flask. You want to leave just a little bit of volume left in there, okay? But this is how you would collect the boiling point of your unknown, as well as purify your unknown if it's a liquid. Okay? So then, next part of these steps is we need to be able to have a way to test for our alkyl halide, and the way we do that is a flame test. It's called the Biostine flame test. So instead of doing qualitative analysis for qualitative elemental analysis, we're just going to test to see if there is a halogen present or not, okay? And then in what you do otherwise, you can figure out, based on process of elimination, what halogen you have. So this flame test, you're going to use copper wire, and you want to clean the wire just like you clean the nichrome wire in Gen Chem when you were doing flame tests in Gen Chem. Clean the wire in a flame, and then when you stick the copper in an organic material that has a halogen in it, the reaction in the flame with the copper produces a green flame. So you'll get kind of probably poof of some flame and soot, and then you will see a green flame if you have a halogen present. And so that's what you're looking for. And we'll demo what that's going to look for with a known halogenated compound in lab this week, okay? But that's how you would check for your alkyl halides. The next thing you need to determine is what is your unknown soluble in. And so there is a table in your lab manual that you follow for determining the solubility. And what you want to do with this table, so this is table 6.1, so it's in experiment 6. What you want to do with this table is you make sure that you follow it in order, okay? Because it's really important that you pay attention to whether things are soluble or not as you go along in the table. So for example, this top row here, you always start with water, see if it's soluble or not. You have an unknown that is soluble in water, but not soluble in ether. Well, then if you have something with that solubility pattern, you wouldn't go on to test the 1 molar HCl, the 2 molar NaOH, or the concentrated sulfuric acid, because it tells you not to do those tests, okay? So make sure you follow the table in the order that it is given, and if you get a pattern where there's going to be some solvents you don't test, then don't test those solvents, okay? You're going to use about 1 milliliter of the solvent. You don't need a lot to be able to test solubility. And then a couple drops or a little bit of, if you had solid unknown, a little bit of the solid to test if it was soluble or not. So you're looking for, does it go into the solvent? Is it completely dissolved? Or is it floating around in the solvent, not completely dissolved, okay? With sulfuric acid, if it reacts, it's soluble, okay? So if it turns yellowy, almost sometimes orange color, and the drops or unknown that you put in there have disappeared, count that as soluble, because it's now gone on and reacted with it, okay? All right, so make sure you follow that table for the solubility properties. Then what you will do, get this guy on here a second. And we're going to talk about this in more detail here in a little bit. You need to look at the IR spectrum that you are going to collect. And so the IR spectrum is going to help you figure out the functional group or chemical class present in your unknown. So it'll help you figure out what these guys are. So here, look at this real quick. once you have collected your IR spectrum, you're also going to compare your IR spectrum to a literature IR spectrum, okay? And so one of these is STBS, Spectral Database for Organic Compounds. And it's a Japanese website, so if you just Google STBS, you will get to this spot, and you have to agree to their disclaimer. I did. I thought I did. And then what you will do is you will have a list of compounds to look up, and I'll show you here in a minute how you come up with this list of compounds. You will put these in here and then look for different spectra. So let's say I typed in 1-bromopropane. Under IR, they do have spectra available, so you click on that, and then you would see what literature spectrum they have for the IR spectrum. And what you want to make sure you always get when you're looking for these literature spectra is you want something that says liquid or neat. You don't want to get a vapor spectrum, or you don't want to, let's see if this has a possibility. Sometimes there'll be spectra that are in a solvent. You want to make sure up here or on the spectrum somewhere it tells you that it's a liquid spectrum or a neat spectrum. Okay? All right, so now something else you can use is any computer lab that's a campus computer lab, so like the one we use for WebMO 3101, but the Duck Lab or in any of the dorms, has the next program I'm going to show you. So under all programs or all apps, under chemistry is Aldrich Spectral Viewer, which is this program here. And so to use this program, first search under the question mark, and so we would type in our 1-bromopropane, and then say execute. No, it doesn't want that one. Let's try. It's lying to me. Let's try something basic here. There we go. Okay, so looked up propanol. We'll go with 2-propanol as being okay. So hide the search results, and then, oh, that guy doesn't have, it's being very, very unfriendly today here. Let me try. See if we can get something that has an IR spectrum. Okay, butanol did. So you, up here, it's showing you NMR spectra as its default, which you'll use second semester. To get the IR spectrum, you just click on IR, and then you have the IR spectrum. And here it says neat, or it'll say liquid. Then what you do to get the peaks marked, the other spectrum had a table of peaks that you would print out. Here you raise and lower, so I clicked on this guy, and then I clicked on this threshold. You raise and lower the threshold, click on it, and then the peaks below it are marked. And then when you go to the print icon, you say print the peaks on the spectrum, it would print it on the spectrum. So you would have the literature spectrum with the peaks printed on it, okay? All right, so then another website that you can use is Webbook. So I'm just going to write this here. So it's Webbook with 2 B's, NIST.gov/chemistry. You can also look up IR Spectra there. However, Aldrich Spectral Viewer and STBS are going to have ways for you to look up the specific frequencies for the spectra. This guy does not print them with the frequencies on it, okay? So I tried the other 2 options first, all right? And so in a little bit here, we're going to talk more about what you're looking at with the IR spectra. The fifth thing you will use is chemical characterization tests. And so these tests are specific for specific functional groups, and so it will help you figure out, again, functional group or chemical class. And so what should happen is you should be able to interpret from your IR spectrum what you think the functional group is, and then you should be able to do chemical characterization tests that help you verify that, okay? And so there's 4 different tests in addition to doing the flame test. Basically, the flame test is our characterization test for the alkyl halides. So, first one of these is our bromine test. And this one is a little bit tricky because what you're going to start with is if you have an alkene, most likely it's going to be a colorless liquid just based on the nature of the compounds that we have for this experiment. So it's going to be colorless. You're going to add bromine to it, which is red-brown, okay? And what you will get is something that is colorless. So it kind of looks like you're going from colorless to colorless, nothing's happening. If it stays colorless, actually something is happening. So if you have alkene, add bromine to it, it is reacting here to give the dibromide, which is colorless, okay? And so what you're doing is you're counting how many drops until you get that bromine color to persist, because the bromine color will persist when you've run out of alkene to react with it. So when there's nothing left there to react with, then it's going to turn orange. When you get to like 20, 30 drops, that's enough bromine. You don't need to keep adding it until you get that bromine color to persist. If you've added 20 to 30 drops, you could consider that potentially a positive for your bromine test. Okay? Now, another reaction that happens with the bromine, so there's another piece to it besides just counting drops, is it can react with alkanes as well. Say you have an alkane, reacted with Ir2, and you need a little heat or light for this to happen, but you're not completely in the dark in organic lab, so that's enough light for this to happen. And what you will get instead of that addition across the double bond, you will get a substitution reaction, and it will substitute for that proton, and then it'll give off HBr. And so when you are testing, the reason that you use pH paper when you do the bromine test is to see if you give off this HBr gas, which will give you red pH paper, okay? And typically, this will turn orangish color sooner than reacting with an alkene, okay? The thing that gets a little bit tricky is with that pH paper, you can get false positives. So don't use pH paper as the reason that you are saying that you absolutely have an alkane and not an alkene, okay? Don't use those results alone, all right? Now the thing with the bromine test is you actually need a second test to be positive in order to say it's an alkene. And that second test is the potassium permanganate test. And so you'll have your alkene, again, colorless, dissolved in acetone. You add 1 drop of potassium permanganate, which is really deep, like most of you used it in Gen Chem last year, that deep, almost black purple color. 1 drop of it, and it will react across the double bond to give you the diol. It also forms manganese dioxide. So you're decolorizing because you're getting this reaction of the potassium permanganate reacting across the alkene, and you're forming this solid, which is a brown solid. So what you should see with this test is you add that potassium permanganate. At first it's purple, and then that purple starts fading and either going away or turning, more red, pink color, not so purpley. And then you start seeing signs of this brown solid forming. That's a positive potassium permanganate test. So for the alkenes, you need both bromine and potassium permanganate to be positive to say that you have an alkene. And this test, you want to give it about 3 to 5 minutes, more probably about 5 minutes for it to react. So don't just sit there waiting for something to happen. Add the potassium permanganate, set it to the side, and then come back in a few minutes and look at it. So going back to with the bromine test, and is it reacting with an alkene or is it reacting with an alkane? If you have a positive bromine test and you have a positive potassium permanganate test, most likely you have an alkene, even if that bromine test gave you a little bit of acidic pH paper. So that's why I was saying, don't bank everything on the pH paper. Okay? Use your other results to help you figure out what's going on there. Okay? So those are the first of the two tests. For a ketone, we're going to use what is called 2,4-dinitrophenylhydrazine. So say we have a ketone here. This is our 2,4-dinitrophenylhydrazine, this big guy here. And it is in sulfuric acid and ethanol, so be careful with it. You don't want to get it on you. Wear gloves with it. And back to the bromine, keep that in the hood. You don't want to inhale any of the bromine or carbon tetrachloride fumes, so keep everything in the hood. Wear gloves as well. When the ketone reacts with the 2,4-dinitrophenylhydrazine, you form what is called the hydrazone. So this part here is our hydrazone, and it gives a yellow-orange solid, okay? And sometimes you have to heat them. Sometimes they don't turn color right away. But you should, depending on the ketone, it should be either yellowish or yellow-orange that you see if you've got a positive result. And there's only one chemical test for that, okay? Then the last of the chemical characterization tests is a Ceric ammonium nitrate test, which is going to test for alcohols. This is also known as a CAN test. And there's not really a reaction to show with it. It's a complexation of the Ceric ammonium nitrate. So this is our Ceric ammonium nitrate. There's the ammonium piece to it. And the cerium, and then we've got 6 nitrates with that. And what happens is when it is in the presence of an alcohol, it forms this complex. So you've got the cerium complexing with the oxygens of the alcohol. So you've got something like that. And it forms this complex, and this complex is a red or red-orange color. You're going to see the color change when that complex forms, okay? So there's not really a full reaction to show. You can just say that there's a complexation that takes place with the Ceric ammonium nitrate, okay? But it's that complexation that gives you the color change, okay? So those are the 4 chemical tests we would do besides doing our flame test. So then the 6th piece to all of this is then doing a literature search of the chemical class. So in the back of your lab manual are lists and lists of compounds, okay? And they are broken up by functional group. So you need to know the functional group, and then you need to know either the melting point or the boiling point of your unknown, okay? So it's first divided by functional group, and then it's in order of melting point and boiling point of those unknowns. And what you want to do is look plus or minus 10 degrees of your melting point and your boiling point at all those possible compounds, because those are the possible compounds for what your unknown could be, okay? And so once you've gone through all of these pieces and gotten down to what is definitely the functional group present in your unknown, you go to the back of your book, look in the appendices, find that chemical class, find the area of the melting point or boiling point, and then you're going to look up the literature Ir spectra of the compounds that are plus or minus 10 degrees of your melting point or boiling point, and then find what matches, okay? And so in a little bit here, we'll talk about what is considered a match, and I'll show you examples of what matches and what doesn't for things that you're looking for in terms of Ir spectra, okay? But when we're talking about a match, you do want it to match, and it will match, the whole spectrum will end up matching, okay? Now there's also a book in 3123 that can help you with that, and that is, I always forget its name, the Handbook of Tables for Organic Compound Identification. It is the same sort of thing. It's arranged by chemical class and then melting point and boiling point order. So you could use that as well. The one thing with it is just be really careful because it's seen lots of use in its years. All right. So now let's talk about pre-lab, and then give you an example of the flow chart for today, and then we'll look more specifically at Ir spectra so we can get back to how we're going to make things match for you. So the pre-lab for experiment 6, it's going to have most of the basic pieces that you usually have in your pre-lab. You're going to have a purpose, and again, it's for experiment 6. So you're writing the purpose for experiment 6. You're going to have the chemical test reactions. Those are your reactions, okay? You're going to have physical data table for the chemical test and solubility test reagents. You're going to have a flow chart, and the flow chart is it's unlike other flow charts where we focus on having these branched arrows and showing all the separations for the workup and so forth, because this is a different type of experiment. Your flow chart is in your lab manual on page 612. Or figure, actually I believe that page number is wrong. It's look for figure 6.2, okay? You have your unknown. You're going to visually look at your unknown. What does it look like? Determine the melting point or the boiling point in the flame test. Don't worry about sodium fusion. We're just doing the flame test. You're going to determine the chemical class by solubility test, interpretation of the Ir spectrum, and then go on to reinforce what you find here with the chemical tests. And then you're going to search the literature for compounds with similar chemical, physical, and spectral properties, and then decide what your unknown is. What is the specific identity of your unknown, okay? So this is the flow chart that you're going to use for experiment 6. Then you'll need to show new equipment. That's your all-in-one simple distillation apparatus. And then number 6 is references. So what you don't have is a yield calculation because there's nothing really to take a yield or percent recovery or anything like that, okay? So those are the 6 parts that you should have for the pre-lab, okay? All right. So now let's talk about IR spectroscopy so you have an idea of what you're looking for with those spectra. So as you probably covered in Gen Chem, visible spectrum, electromagnetic spectrum, and Gen Chem. And the visible spectrum is right between the ultraviolet and the infrared spectrum, okay? As far as energy, infrared is much lower energy than ultraviolet. So what we're looking at with the infrared spectrum and what is happening as your compound is absorbing infrared energy is what is happening to the bonds as they absorb the energy. So the, pull this back down again. That infrared energy is being absorbed by the bonds, and so it's doing different things with those bonds, and the spectrum is characteristic to whatever particular bonds are in the spectrum, okay? So there's stretching, and there's scissoring, and there's rocking, and wagging, and twisting, all sorts of different things that are happening with the bonds as they are radiated with infrared energy, okay? And as they are absorbing that infrared radiation. So it's not like UV energy or UV radiation where you're actually getting electrons to move, things like that. We're just getting some movement along the bonds, and depending on the type of bonds that are present, that is the different types of movements that they are going to be using, okay? Or we're going to be measuring. So within the span of what we are going to be looking at with the infrared spectrum, we're looking at from 4,000 to about 600 inverse centimeters, or what we call wave numbers. That is the frequency that we're looking at. You've got some stretching and bending that is occurring, mainly stretching here, and then we get into bending here. And then into the fingerprint region, you get more into like the wagging, this twisting, the rocking, scissoring, things like that. As far as looking at things that we can use to diagnose what is in a particular compound, we're usually going to be looking from about 4,000 to about 1,350 or so, okay? So this fingerprint region we'll talk about here in a little bit, why that is important, but we won't be identifying what different bonds are causing what's happening in the fingerprint region, okay? All right. Let's back up. Okay, so at the back of the room, you have a yellow sheet you should have picked up, okay? Or if you didn't pick one up on your way out. And I'll also post it on Moodle as well. To start with, as far as interpreting IR spectra, this is the sheet that you're going to use as kind of your baseline for what you're going to use to interpret the spectra and what you should be looking for in that interpretation. So if you look at the frequencies, they all fall in that 4,000 to 1,400, 1,350 range, okay? And so you do want to become familiar with, okay, what is the range for CH stretching and OH stretch, all these different functional groups, primarily the ones that are important to this experiment. So things, CH stretch, the SP3s are going to be only our alkanes or alkyl halides. The SP2s would be then our alkenes. The OH stretch for the alcohols, the C double bond C stretch for the alkenes, the C double bond O stretch for the ketones. So start learning those, and eventually we'll learn most of the rest of the pieces of this, okay? In the back of your lab manual, there's much more detailed tables of different characteristic IR absorptions. So as we go into more complicated experiments, you're going to be using those as well. But start with this table for experiment 6, okay? Now, in your McMurray text, you have a very similar table. It's just, it doesn't list things as broadly, it's more specific in where the frequency is for those different stretches and bends, okay? So this is table 12.1 in McMurray is going to give you basically a similar type of information, okay? So now let's look at different examples of what's going on in these different, with spectra of different compounds with different functional groups. So the first one I have is cyclohexene, and so it is an alkene, okay? And so this is a characteristic spectrum of an alkene because around 1600-ish, we've got this C double bond C stretch, right? And then we also have an sp2CH stretch. Now this guy is sometimes hard to see. Sometimes it's tucked more up almost in the baseline and kind of hidden by this other part, which is the sp3CH stretch. Is more in the 2800 versus sp2CH stretches in the 3000 wave numbers, okay? So if you decide that you have an alkene, you should have a similar IR spectrum to this, okay? Here is an example of an alcohol, and something that's really characteristic with an alcohol is this broad, large stretch of the OH stretch, okay? And so, or broad peak of the OH stretch, and it's usually in the 3500 to 32, 3100 region, but it's this huge stretch that is unmistakable, okay? And so if you have an alcohol, you should definitely see this in your IR spectrum, okay? Now, other things that you would want to identify if you have an alcohol is, again, your sp3CH stretch, because you still have probably sp3CH carbons, like here in butanol. And then look at also the CH2, CH3 bending that's on your yellow sheet, because that's down in this region. And you would see some of that with an alkene as well. Now with a ketone, really characteristic of a ketone, so that's C double bond C stretch was not as an intense as this ketone stretch. A carbonyl stretch in an IR spectrum is very intense. So if you have a carbonyl present, it is going to be a very intense peak in your spectrum, okay? Now, sometimes what happens, is, especially with alcohols, you can get, your alcohol can oxidize to a ketone, to a carbonyl. So you'll see the huge OH stretch and a little carbonyl stretch. That's probably impurity in your alcohol, not that you also have an alcohol and a carbonyl, okay? If you have a compound that contains a carbonyl, and it's supposed to, it's going to be in a very intense stretch, okay? And so you would mark that, you would mark your sp3CHs, and again, you can mark your bending down here. Now here's an example of an alkyl halide. The alkyl halides, the characteristics peaks in an IR spectrum for an alkyl halide is down in this fingerprint region that we're telling you you're not responsible for being able to label, okay? And so you're not going to label something specifically for an alkyl halide. You're going to label the sp3CH stretch, and then you want to verify that for sure that Beilstein flame test was positive, okay? Now, if you think you have an alkane, make sure that you definitely have a negative Beilstein flame test, because that's the only way to tell the difference between the two of those functional groups, all right? And so here's an example of an alkane. Again, it's just sp3ch, so there's not really any difference between this and it being, chloropentane, okay? Now, here I'm going to show you why that fingerprint region is, okay? So I've got hexane, we've got a 6-carbon compound, and we also have a 6-carbon alkane, and I also have 2-methylpentane, another 6-carbon alkane. So when you look in the diagnostic region, there's really not much difference between the two of them. You're not going to be able to tell the difference between your hexane and your 2-methylpentane. Where you tell the difference is this fingerprint region, okay? So when you are looking at spectra and you are deciding if something matches the spectrum that you have, it needs to match in the diagnostic region as well as the fingerprint region, okay? If it doesn't, then it's not a match. And as far as a match, you should see the same peaks at the same frequency with the same relative intensities. Now, pull one of these up. Say you see this spectrum, but all the peaks are shifted up a little bit. That has to do with how much sample you have, not the intensity of the peak. So it's the relative intensity of the peaks that you're looking at. So if you had all these same peaks, all the same relative intensity, everything was just shifted up a little bit, you have a little less sample than the sample that was used to collect that spectrum, okay? So that is what you're looking for when you're trying to decide if you have a match or not. And so the matches are going to come from the SDBS, the Aldrich Spectral Viewer, the web book, or there are paper indices in 3123, but exhaust your computer databases first before you go to the paper indices, okay, because they get sometimes a little bit more confusing. Now at the back of your lab manual, back of experiment 5 is an example table for IR spectra. And whenever you are collecting an IR spectrum in an experiment, you're going to show a table similar to this for that compound, okay? So you're going to use this table for experiment 6, and then most of the experiments that we do the rest of the semester, we're going to be collecting IR spectra. So you will be reproducing this similar type of table. So you want to give a list of the frequencies of the peaks that are present in that spectrum. If you have a literature spectrum, which experiment 6 you do, to compare to, you will list the literature frequencies, give the intensity, the shape, what is the bond or vibration that it is corresponding to, and then which, comment on differentiating it too. So like the CH stretch, there's multiple CH stretches. There's sp2 CH stretches that are usually in alkenes, or sp3 CH stretches that are part of alkanes. Here we've got some impurity due to air. The C double bond C stretch is due to an alkene. So that's the type of comments that you are going to give. But you want to put this table in your notebook, and you want to put it in whatever you are physically turning in. So experiment 6, what you are physically turning in is there's a report sheet at the back of your lab manual, so page 615 and 616. You've got a report sheet that you're going to fill out the different pieces, so name, unknown number, what does your unknown end up being, what is the name of it, physical properties, melting point, boiling point, what happened with the flame test, what happened with the solubility test, which this can be a table, just like the table you used for the solubility test. And then you can explain any differences or other observations you had. Results of the chemical test, and then this table is exactly like the table that I just showed you for recording your IR spectra. So for experiment 6, we've already got it on your worksheet for you, but you should also put it in your notebook. And then you're also, for experiment 6, going to attach a conclusion, which we'll individually talk to you about, okay? So just don't forget this part. A lot of times students, after experiment 6, forget for experiment 7 that you still need that table. Okay. Questions? Okay, that is it for this one.